Our next presenter is Gopal Gupta, who is professor of computer science in the University of Texas. And Dr. Gupta, like Peter was, devoted his life to artificial intelligence. And his current interest, probably a little bit contrary to Peter, was devoted to not human-like, but what he calls human-style common sense reasoning. And being in academic world, probably it's a little bit easier from commercial perspective to conduct research without worrying too much about financials, but still it gives him enough resources to do serious research and development. And probably we will see more specific results in direction of cognitive AI. And let's listen what Professor Gupta will present today. Thank you very much, by the way, for doing this again at DecisionCAMP, and you're always welcome.
Yes.
Okay.
Thank you so much, Professor Dr. Feldman. And yes, thanks for the opportunity and giving me the time slot. So, it's great to be, giving a talk here. So you can see my talk is titled Building Trustworthy AI Systems and how we can essentially use automate common sense reasoning for bringing in trustworthiness into AI systems. So what I'll do is, I'll build up the background a little bit. So the beginning part, you may already know, thought about it before or heard before. So I'll go over it very quickly. I also run the Center for Applied AI and Machine Learning, which actually is an industry-facing center where we actually take on projects with companies and help them solve it. Essentially, we're sort of R&D center for companies that don't have one. Has to involve research, otherwise it's not that interesting for us. In the past, my research has been supported by many of these companies as well as the usual NSF and DARPA and others. So let's start with what is intelligence, what is artificial intelligence. So intelligent reasoning by computers has been a goal of computer scientists, of course, ever since computers were first invented in the 50s. So the question that I ask is, okay, what is intelligence? So intelligence, you could argue, has two broad components. So first one is that we have the ability to learn. Now, of course, we could be taught as well, but this learning involves uh, generalizing or looking at patterns and learning from those patterns. And of course, if we automate it, we get what is called machine learning. And of course, the idea of learning is to acquire knowledge. And then once we acquire this knowledge, right, whatever we learn, the pattern or whatever we observe, sits as knowledge in our mind, and then we apply this knowledge, which is reasoning. So reasoning is the other half of, I would say, intelligent behavior. And if we automate it, of course, it's automated reasoning or machine reasoning or whatever you want to call it. There's of course vision, speech processing, speech generation, etc. But by and large, you could say that it's learning and reasoning. That those are the two components of intelligent behavior. So of course, AI has been receiving a lot of attention. I mean, some of us who have been around for a long time, very pleased that, right, AI. And of course, when people use the term AI, what does it mean? So the question is AI, machine learning. So before the advent of, Chat GPT and all these tools, when people said AI, like, 5, 7 years ago, AI meant, machine learning or deep learning. And then of course, today, maybe when you say AI, they probably mean, when people say AI, they probably mean, things like large language models. And then of course, there's the term AGI, artificial general intelligence, which is human-like intelligence. And then a lot of people think, generative AI is essentially AGI. So of course, as we all know, many of us have been around for a long time in the field. So for the first 40, 50 years, generally when people said AI, it was equated to automated reasoning. But today the pendulum has swung the other way. And when people say AI, they actually mean machine learning or deep learning, or maybe even just generative AI. Of course, research on both machine learning and automated reasoning started, long time ago. So, and again, you already know what is machine learning, from positive and negative examples, learning a concept from a positive and negative examples. And there is supervised learning, unsupervised learning, reinforcement learning. We could call that predictive AI. And then, of course, you have generative AI, which I'll talk a little bit about later. So first 10 slides are trying to build up the background. So I'll go very fast. What is automated reasoning? Again, we know that given pieces of information, we deduce new knowledge, draw new conclusions. So, for example, we know that all humans are mortal. We have this information, and that Socrates is a human. Then we can conclude that Socrates is mortal. And of course, machine learning has a long history as well. Bayes theorem. So based on Bayesian networks, Markov chains, least squares, probability theory, perceptrons, neural networks, all these have been around. So Bayes theorem was discovered, for example, in 1763. So, a long time back, perceptrons in 57 and so on. And today we have neural nets, deep learning, large language models, etc., etc. Automated reasoning has a long history as well. In fact, even longer. So logic and inference procedures play an important role here. And it goes back to time of Aristotle, and there is even ancient Indian work on formalizing logic called Nyaya. And then, of course, you have 1850s George Boole and Gottlob Frege, predicate logic set theory. And today we have advanced theorem proving systems, logic-based programming languages, and advanced rule-based systems, foundation. And of course, foundation of much of traditional computing has been in logic. So computing science, now, of course, data is playing an important role. So you could say, well, computer science and now data science. So but there have been many successes, as we know. We know, for example, Deep Blue system that beat Gary Kasparov, the 90s, I think. Then Watson around 2010s wins Jeopardy. So Deep Blue was purely reasoning research, um, what we would call automated reasoning. And then Watson, of course, combined reasoning and machine learning. And then, of course, now there are systems that are purely based on, you could say, machine reasoning, such as AlphaGo, AlphaZero, large language models that purely based on pattern matching, and even self-driving cars today. The basic technology that is used is machine learning, such as the FSD in Tesla. Now we know that machine learning has had tremendous success, and again, phenomenal technology, but it has many limitations. It can give wrong answers because the model that is learned by a machine learning system is basically an approximate function that maps features to labels. So approximate here is the keyword. You need lots of handcrafted data. Each narrow application needs to be specially trained, at least in predictive AI. And then explainability, interpretability is a problem, as we know very well. The systems are opaque, making it very hard to gain insight and not well suited for high-level symbolic reasoning or planning. And of course, computationally very expensive, whereas we humans use only apparently 12 watts of power. And then again, you have probably seen this where we put a little bit of tape. So again, limitations of machine learning, little bit of tape on a stop sign, and self-driving cars are unable to recognize that it's a stop sign, and no human will have any trouble. And similarly, you take a picture and you add some noise to it, and the machine learning models that been trained on these pictures basically give wrong answers. So if you have a bus and then you add some white noise, it might think that what it's seeing is an ostrich. And then, of course, problems with explainability, the very popular example where you have to distinguish between a wolf and a husky. And then the machine learning system essentially figures out that wolves always have snow in the background. So then it starts predicting whether it's a wolf or a husky based on whether there is snow or not. So if you have a husky with snow in the background, then it says it's a wolf. So of course we have no idea because it's a black box. And then of course autonomous vehicles largely based on machine learning technology, and the uh, you could say largely has not succeeded in the sense that the goal was um, to have full autonomous driving, but that has not been achieved. And there are many comments here from various people who have been involved in the enterprise. And the most interesting one is that we were promised complete autonomy by 2018, but in I think 2023 or 24, Tesla argued in a court, when they were sued for something, that the broken promises for autopilot system or autonomous driving system was a failure, not a fraud. And I think they reached the level of, so there is a scale from this and I think Tesla at like 3.5. So, and of course, we have generative AI systems. You already know, most of you, right, are very well versed, amazing technology. You can generate poems, etc., generate pictures, and so on. You can tell it to draw me a picture of draw me an Egyptian painting of two people arguing over whose turn it is to take out trash, and it does a great job, so on. And of course, we know how it works. It works by predicting the next word. I mean, it's more complicated than that, but it boils down to predicting the next word. So, so essentially, it's a pattern matching exercise. And then we know that, it has, since it's based on pattern matching, predicting the next word, it cannot really do reasoning very well, or it can only do reasoning that is embedded, in the text. So, and there are examples where, it gives a wrong answer. So my favorite one is where one car is traveling to Dallas at 40 miles per hour and travels a distance of 14 miles. Another car starts at the same point and travels the same route at 80 miles an hour. So both cars travel the same distance. One travels at doubles the speed. How far does the second car travel? Then it will do all this calculation and tell you that it covered a distance of 28 miles. Because the answer is obviously, they went from the same point to the same point. I mean, they basically traveled identical distance, so it should be 14 miles for both. But because second one traveled double the speed, based on pattern matching, it calculates, 28 miles. Now, as we know, these models keep improving. So you try it today, maybe it may not work. Or if you ask it to generate a picture, draw me a picture of a clock. This was going around on LinkedIn, right, a few weeks ago. And it will generally will give you a clock showing 10 past 10, because that's the most, if you see a picture of a clock, generally the arms will be shown at 10 past 10. So can large language models do it all? So people say, well, large language models are going to get us to artificial general intelligence. Can machine learning and large language models achieve artificial general intelligence or artificial super intelligence even, right? Can LLMs be trustworthy? And I'd say the answer is no, because LLMs lack awareness. They don't know what they know and don't know, right? They have no idea. It's all purely pattern matching device, essentially. Predict the next word, predict the next word. It's amazing that it works so well. So we can think of machine learning as sensing or pattern recognition, right? And that's what LLMs are, also sophisticated, pattern matchers. And I would argue that you know, of course, humans and animals also use pattern matching through sensing and pattern matching. And in fact, animals are much better than us at sensing and pattern matching. So, for example, um, eagles can see better, right? And dogs can smell better, and camels can smell water because there is some molecule in the water, some bacteria in the water that travels in the air 50, 60 miles. So they can actually sense water 50, 60 miles away. And as humans, we don't have those kind of sensing capabilities, or even animals can see, right? Spectrum, part of the spectrum that we don't see. But why do, humans sit on, you could say, top of the evolutionary chain? And the reason is that we have reasoning capability. So these animals lack advanced reasoning capabilities. They have some. And as you go up the evolutionary chain, you see that reasoning capabilities improve. So if we want to achieve AGI, I would argue that you need reasoning capabilities as well, as in deductive and abductive reasoning capabilities. So essentially, better reasoning capability means higher intelligence. So two different ways in which brain processes thought is probably already familiar with this, famous book, Thinking Fast and Slow by Daniel Kahneman. And that's where the title of my talk comes from. The word slow refers to the slow over here. So system one thinking is essentially intuitive fast thinking based on recognizing patterns using our senses. So for example, if I hear the sound of a siren, right, then if I have heard the sound of a siren before, I can instantly recognize it. I have no problem in recognizing, a chair or a table. I mean, it's effortless. And now, uh, uh, with the sound of a siren, for example, recognizing that, there is no way you can explain to someone how a siren sounds like. You have to hear it, right? So you have to hear it by recognizing the pattern. And that's one of the problems of explainability as well, that some of these things are inherently unexplainable. How do you explain the sound of a siren, what a siren sounds like, right? Then, of course, once we so we learn to recognize the sound of a siren, and that's the only way. Then you have system two thinking, which is slow or deliberative thinking, which is based on reasoning, or I would call common sense reasoning, human style common sense reasoning. Um, so fast thinking can be thought of as obtaining sensory input, and then we use our instincts to draw conclusions. So this is how most animals, you could say, operate. But they do have maybe some rudimentary reasoning capabilities. But most of it is. There's very interesting, actually, video of this albatross, where the albatross, they nest on, like places that are 4 or 5 feet, 3 or 4 feet, maybe even 2 feet off the ground, and they lay their chicks eggs over there, and the chicks hatch. When they come back, because of wind or storm, if the chick falls off the perch, even though it is just 1 feet away, the albatross cannot recognize its chick. And unless the chick climbs up on the, where the albatross, left it, the albatross cannot, the chick will not survive. So you can see that it does not have any reasoning capability when it comes to that, if the chick is not there, maybe it would have fallen off. And you actually can Google it and watch the video. It's there. It's amazing. So animals use sensory input and their instincts to draw conclusion, and slow thinking is the way to do things, in a more, where we have to actually reason, and your reasoning is verifiable and explainable. So we automate system one thinking, we get, what essentially is machine learning. Automate system two thinking, and we essentially have automated reasoning or common sense reasoning, right? So think of it again, taking my example about siren sound. So in North Texas, if you hear the sound of a siren, then it means, and the weather is bad, then it means that there is a tornado or something. So you have to find a safe spot. Then figuring out where the safe spot is the deliberative thinking. You have to think very carefully, what is the space that has, think about your house, you're laid out, and find the room that has, maximum number of walls between that room and the outside, and so on and so forth. And uh, so we use both, basically, our fast thinking and slow thinking, essentially, to survive in this world. So another interesting fact is that, so we could say that maybe large language models can get us to AGI. However, neuroscientists have shown or strongly believe that uh, language, so I have highlighted, language does not appear to be a prerequisite for complex thought. It plausibly co-evolved with our thinking and reasoning capacity. So basically, part of the brain that processes language is different from part of the brain that actually does rational thinking or thinking. And the reason they can discover this is because there are people who have had a brain injury and they lost part of the brain, which processes language. So they cannot talk, or they cannot. So essentially, what this is saying is that just language processing cannot produce, uh, you know, reasoning. You have to have that reasoning module. There's a separate reasoning module. So language does not appear to be a prerequisite for complex thought. It plausibly co-evolved with our thinking and reasoning capacity. So those are two different things. So essentially what I'm arguing is that you need a large language models, which purely are language processing devices, cannot lead us to AGI. So if we look at how we operate, we essentially take sight, sound, smell, all the sensory inputs, and maybe text, reading text. We convert that, using our pattern matching abilities into knowledge, which resides in our mind. And then we, of course, possess a lot of common sense knowledge that we have built over a number of years. Then we check, one of the things we do is that we use our common sense knowledge to check that the knowledge we have obtained from this sensory input is consistent and complete. So for example, if I say I have an 8 foot tall daughter, you immediately know that I'm lying, because you have this knowledge that people generally are maybe 7 feet tall, exception, but generally people are, have, this kind of average height, so on and so forth. So you're always checking the consistency of the knowledge that, uh, we are acquiring, or we are uh, receiving based on, or receiving based on our based on the sensory input, based on our senses. And then we also check that this knowledge is complete, in the sense that we may seek more information, right? We see something and then we may take a closer look, or if we are talking to someone, we receive partial information, we may ask more questions. Once we have done that, check for consistency and completeness, we'll draw some conclusion, and then maybe we'll take some action. So what I want to do is, or what we want to, our group wants to do, is to automate this this process. So essentially use machine learning for converting sight, sound, smell, touch, taste, text into knowledge represented as logic predicates. And then I must have a way to represent common sense knowledge and a reasoning engine, common sense reasoning engine, that will check the consistency and completeness of this knowledge, draw conclusions, and then take actions. So this is actually sort of realizing this computational representational understanding of mind that cognitive scientists have proposed. So we do need this, this knowledge part, this awareness part, that, in order to build trustworthy systems where we can check for consistency and completeness. So we look at the current approach in AI, everything is tackled at the system one level. So even people build these question answering systems where you want to answer questions against, say, a picture. Then you collect training data, you collect thousands of images. With for each image you have sample questions and corresponding answers. Then you train a model, and then given a new picture and a question, you throw it to the model and it gives you answers. Very much like, for example, how a uh, autonomous car might operate. It's basically, its cameras are looking at the scene, analyzing it and learning from it, and then figuring out, using its model, what is the next action, so to speak. So for building trustworthy AI system, we propose to use machine learning for system one, type thinking, and automated common sense reasoning for system two, type thinking. And that's what will give us the accountability and trustworthiness. And in fact, even if you look at, um, when we try to explain something that we have seen. So for example, if you ask me, I look at a cat and say, why is this a cat? Then I would say, well, it's got whiskers, it's got ears. So generally, we give an explanation, based on some kind of reasoning process. So reasoning is extremely important for trustworthiness in AI. So I believe that to build trustworthy systems that are capable of reaching AGI, we have to emulate humans. Use machine learning, large language models, generative AI for discovering knowledge, where discovered knowledge is awareness. So that's basically the knowledge that we acquire from our senses. And then use automated common sense reasoning for processing this knowledge, where processing means checking consistency and completeness, using reasoning, and then drawing conclusions. And you could say that the consensus is that machine learning systems have sort of hit their limit, and common sense reasoning is needed. And many researchers have said that we need reasoning as well. And people suggest neurosymbolic systems, AI systems. And the picture the diagram that I showed essentially is kind of a neurosymbolic system, that special type of neurosymbolic system that combines machine learning and reasoning. But the question is, how do we automate common sense reasoning, or slow thinking? How do we automate slow thinking? And that's what I'm going to address, the next maybe 10-15 minutes. And then we'll talk about some of the applications, and then, open for questions. So why do computers have trouble in reasoning while humans can reason about things effortlessly? And as I said, human brain just uses apparently 12 watts of power. So what are the characteristics of human style reasoning? So our reasoning is non-monotonic. We can revise earlier conclusions in light of new information. Classical logic, unfortunately, breaks down when there is a contradiction. So the classical example, Tweety is a bird, does it fly? We jump to the conclusion, yes, it does. But then if we learn that Tweety is a penguin, we withdraw. That penguin type of birds, that birds fly, but penguins cannot fly, and then basically break down. We also, connected to this is that we also jump to conclusions and we draw conclusions in absence of information. What, is basically default rules or where we jump to a conclusion, but then we recognize the exceptions to the default conclusion that we are drawing. So for example, we can tell if it is cold outside, then I'll just look outside. I'm inside my house. I will see that if no one is wearing a jacket, then I conclude it must be warm. But of course, those people may be from maybe the North Pole, and for them, maybe 40 degrees Fahrenheit is warm weather, for example. We also do not pursue line of reasoning if it leads to some kind of inconsistency. So we also apply these integrity constraints as we are doing reasoning. So for example, we know that a person cannot sit and stand at the same time. And we also, follow invariants in the sense that we know, for example, that a living person must breathe. And so we might use this. So these are constraints on, the world that we see. And we operate, with following these constraints or reason following these constraints all the time. And even we may draw conclusions that are based on these constraints. We can also deal with multiple possible worlds simultaneously. So, for example, if I ask you, can fish talk like human? You will obviously say no. In the real world, fish do not talk like humans, but there is a cartoon world where the world of cartoons where fish do talk like humans. But we can clearly tell them apart, that there's a cartoon world and there's the real world. And you could argue that machine learning systems will have a hard time distinguishing. So for example, if you have a life-size billboard that has a picture of a car, I'm not sure if, the machine learning system might actually get confused, especially if it's at the road level, that there is a car or not. So humans use non-monotonic reasoning as well as non-well-founded reasoning or assumption-based reasoning in our day-to-day life. And that's been the challenge of, you could say classical logic, how to, account for these things. So negation as failure and assumption-based reasoning are two things that we use. So let's, talk about that a little bit. So a little bit more technical now we're going to become. So let's talk about classical negation versus negation as failure. So what is classical negation? We'll represent it as minus P, meaning that I have an explicit proof that P is false. So I might have a rule saying, for example, minus sibling John, comma Jim, if John and Jim have different parents. Okay. So an explicit proof of falsehood is needed. And then negation as failure is that we try to prove P. If we fail in proving P, then we assume that we'll represent it as not P. Not P succeeds. So not sibling John, comma Jim, we try to prove that John and Jim are siblings. And we may fail because we don't know who their parents are. Then we'll assume that they are not siblings, right? And we use negation as both negation as failure and classical negation, in our, or strong negation, as many researchers call it, in our day-to-day life. So we try to prove the proposition P under negation is failure. If we fail, we conclude not P is true. So fail to prove is negation is failure. Explicitly proving falsehood is classical negation or strong negation. So we use negation is failure all the time. However, negation is failure does make life difficult, especially when it comes to nesting. So I can, for example, make these statements. Paul will go to Mexico if Sally will not. Sally will go if Rob will not. And the question is, who will go to Mexico?
The Lib Dems conference is closed. We heard a little of the leader's speech earlier, all about President Trump and Nigel Farage.
Sorry, I did not get that. Can you say again? So, so the question is, who will go to Mexico? It's very hard for humans to, and we can actually represent this as a logic program, for example, with negation as failure. And then the question is, what is the semantics of this program? And you can see that each rule is easy to follow, but put together, we have no idea, what these rules mean and what is the answer. And that's basically the challenge in knowledge presentation, that we can craft pieces of knowledge that we understand. Individual pieces, easy to understand. Put it all together, we have no idea what it means. So we resort to answer set programming, which is an extension of logic programming extended with negation as failure and strong negation. And many of you may be familiar, with answer set programming. So we have rules of the form P if positive goals A1 through AM, and negation as failure goals not B1 through not Bn. And you can also have facts. P is a fact, and ASP is a popular formalism for knowledge representation and reasoning. The rules could take more general form. You could also have strongly negated goals, and you can have strongly negated goals that have negation as failure in front of them. And we'll see what this means. So applications of ASP have been to knowledge representation and reasoning, planning, all kinds of optimization problems. Really, it's reasonably successful technology. Not going to deal with semantics, and there are many implementations. However, all these implementations are based on grounding the program, transforming it, and then using a SAT solver. So our breakthrough has been that we have this query-driven predicate ASP system called SCASP. So since a SAT solver is used and grounding is used, you can only have data log type programs. These existing systems can only run data log type programs. Whereas SCASP, since it's query driven like Prolog and supports strong negation and negation as failure, um, can even deal with complex data structures. So, so the interesting thing is that because of this limitation, I would argue that ASP has mostly been used for solving optimization problems, not for KRR problems. So now you can actually apply ASP to KRR problems. And also, SCASP also supports advanced concepts such as co-induction, which is needed for assumption-based reasoning or abductive reasoning, constructive negation, etc. Quite a sophisticated system. So consider as an example of ASP, or where you use both strong and negation as strong negation and negation as failure. Consider the college admission process. So we might say X is eligible for admission if X has a high GPA, unless there's an abnormal situation like student has a criminal record. X is also eligible if X is special and has a fair GPA. But right, so for example, an athlete, and again, exceptions apply. So this not abnormal is essentially an exception. Then we can also write predicates for saying when a student is ineligible. So we say X is ineligible, so minus eligible X. If the student is not special, and we know explicitly that does not have high GPA, and we might still have exceptions because, for example, the president of the university might recommend this student, right, even though it's ineligible. And then what happens if neither we can establish the eligibility or the ineligibility? In this case, we say that we must interview the student. So I can actually write rules saying, which tell me what to do if I cannot prove X is eligible, I cannot prove X is ineligible. And that's basically the power of answer set programming, that you can model unknown. What do you do when things are unknown? And so if I have fair GPA John and minus high GPA John, you'll conclude that John should be interviewed. So what basically we get is a hierarchy of sort of, shades of truth. So P stands for P is definitely true. Not minus P represents no evidence that P is false. So possible P. P may be true. Then if not minus P and not P represents P is unknown. So basically saying I have no proof for P being false, I have no proof for P being true. So remember that minus P, you must have explicit rules establishing that P is false. And then not P basically stands for P may be false. There is no evidence of P. And then finally, minus P is definitely false, stands for definitely false. So I would argue that generally we humans do not employ probabilities in our day-to-day common sense reasoning, our day-to-day lives. We essentially use these maybe, true, maybe false. So if I ask you, how was the food at a party? You might say it was good. You might say not good. You might say, I don't know. Or you might say bad, food was bad or not bad, right? Those are the 5 shades. So we can model all this. And essentially this allows us to model human judgment calls. So an example is, and I'll skip to this. So I can, for example, consider a doctor prescribing a medicine M for disease D to patient P. Now, medicine M may have side effect on the patient. What judgment call could the doctor make? The doctor could be aggressive in their reasoning and say, medicine M should be prescribed for disease D to patient P if it cures the disease, and there is no evidence that it has side effects. You may say, well, all the people have seen, they have been fine, so go ahead and take the medicine. Or the reasoning may be conservative, and the doctor may make a judgment call saying, oh, I'm worried that the medicine may have side effect on you, so I must have an explicit proof that it does not have side effects. So I will run a few tests on you to make sure that this medicine will not have side effects on you. So you see how you can essentially model judgment calls. Okay, so let's look at then how possible worlds can be modeled. So this is actually an example from Peter Norvig, who I think posted this in Quora many, many years ago, maybe a decade ago, and said, okay, how can logic model this, So here are 7 statements. People can talk, non-human animals can talk, human-like cartoon characters can talk, fish can swim, a fish is a non-human animal, Nemo is a human-like cartoon character, Nemo is a fish, and we want to know, can Nemo talk? Can Nemo swim? So you see, can Nemo talk? Well, Nemo is a fish. So fish is a non-human animal. Non-human animals can't talk, so Nemo cannot talk. But then we also have Nemo is a fish. A fish. Nemo is a human-like cartoon character. Okay, human-like cartoon characters can talk, so Nemo can talk. So how do we resolve this contradiction? And the reason is very simple. You already guessed it, that we're talking about 2 possible worlds, the real world and the cartoon world. And of course, Nemo can swim in both. So we can essentially ask each statement which world it applies in. People can talk in all worlds, and then I'll just go through it. Fish can swim in all worlds. Human-like cartoon characters talk in only cartoon world. Fish is a non-human animal in the real world, so on. And I can model them as basically, so I'll introduce this, whether we are in the real world or the cartoon world, RWCW. And then I have to state if we're in the cartoon world, if we're not in the real world, and in the real world, if not in the cartoon world. They're mutually exclusive. And now I can actually ask the query, does Nemo talk and does Nemo swim? And in fact, let's see if this will work. Oops, no. Okay, so now we can actually go to the code and run this. So it's already loaded, and this is the SCAS system on, and I can ask talk Nemo, and it will tell me that Nemo can talk, and actually gives an explanation as well, because in the cartoon world and not in the real world, Nemo can talk. And you can see, because it is constructive negation, it'll have all these type of var zeros not equal to Nemo and so on and so forth. Don't have time. And then that's the only world. But Nemo can swim in both worlds. So I can swim Nemo, and it will tell me that Nemo can swim in the cartoon world, which is not the real world, and it can also swim in the real world. So basically, you can do assumption-based reasoning. You can think of this as assumption-based reasoning. Assume that we're in the cartoon world, then Nemo can talk and Nemo can swim. Assume that we're in the real world, then Nemo can swim, but Nemo cannot talk. Okay, now if I can, yeah, okay, all right. Okay, then we can also model complicated things like obligations and prohibition. And again, I'm not going to show you the code. And in fact, we're able to resolve. So we can model deontic modal operators, ought to be the case, this is forbidden, and so on. It actually helped resolve, many paradoxes. So we basically see these obligations and prohibitions as constraints on the world. And once you do that, many of these paradoxes of deontic logic are actually a result that have been standing there for 50 years. So for example, we can model the statement, John is obligated to return his friend Smith car, and the least he can do, so that's a modal deontic operator, obligated, least he can do, return it by noon with the same level of battery charge if it had when he borrowed it. It is permissible to not maintain the same battery level if the car needs a battery change. So you can actually model this and reason over it. What if John wrecked the car, then he did not obviously meet his obligation of returning the car on time. And again, I can actually go to the code, but you don't have time. So essentially, we can think of, so if you want to model common sense reasoning, we just need three things, is what I claim: default rules with preferences, exceptions and preferences, global constraints, and assumption-based reasoning, or those even loops that we saw, CW if not RW, RW if not CW. So automation of common sense reasoning has a long history, and there are far too many systems that I can list here. The most prominent one has been the psych system. But the system is quite complex and closed, and I think complexity actually, I would argue, makes it harder to use. Of course, being closed is another challenge. And so simplicity is very important, and I think we argue that SCAS brings that simplicity, that all human reasoning, common sense reasoning, can be modeled by these three things. And in fact, we have written a paper. So psych authors have proposed 16 desiderata that any, you could say, AGI achieving system must support. And we have shown that SCASP includes all of them. And here is a table. There's a paper on this, not published yet, but on arXiv. So these are the 16. And there are actually two more desiderata that we added. And again, analogy is the only thing that is not supported, but, we are working on that. So let me just, in the remaining, maybe 5 minutes, let me talk about applications. So ASP can model deductive, abductive. So abductive reasoning is essentially assumption-based reasoning that I showed you, the Nemo example, as well as inductive reasoning, the three modes of reasoning that humans commonly use. ASP supports default rules, integrity constraints, multiple possible worlds, and so does CASP in a goal-driven manner. However, implementing ASP is hard, and that's what SCASP does. It realizes the full power of ASP through this goal-directed implementation that supports essentially full first-order logic, or sorry, essentially full predicates with full first-order terms, and freely available on GitLab. So we have applied this to actually, so this has been a long project, maybe SCASP has been around for now 8-9 years. So we've applied it to many applications. So for example, we have automated the guidelines so the way congestive heart failure is treated. There are some 80 to 90 guidelines that American College of Cardiology has come up with that doctors must follow. These guidelines are basically rules. So we actually automated that and worked with some doctors, and we're able to show that this modeling in SCASP was able to outperform cardiologists. Not because the system is better than cardiologists, smarter than cardiologists, but that is because cardiologists can get tired, they will make mistakes, they will forget things, whereas a machine will not. So they might forget that the potassium value has changed from 4.9 to 5.1. And if it's above 5, then that triggers something. And then this technology has been used by Forsante Oy, which is a Finnish company, for automating diabetes treatment management, chronic disease management. And in fact, they have gotten European approval for using this system. And I think it's European approval, like the equivalent of FDA in USA. Then we've also worked on projects where use this model that I showed, where you want to extract medical codes for insurance companies from electronic health records. So electronic health record, basically text is written by doctors and physician assistants, and you want to extract knowledge from it. So if you apply LLM for extracting the code, the correctness is only 60-70%. But if we emulate a human where you use, so basically we use machine learning purely as a translation device from sensory input to knowledge. So we use LLMs for converting text into logic predicates representing the knowledge. And so essentially we're using the pattern matching capability of LLMs, which is extremely good, right? I mean, that's what they are, right? Pattern matchers. So they perform very well. So essentially use it as a semantic parser for extracting knowledge, relevant knowledge. And once we do that and process, do the reasoning just like we humans would do, right? We would look at the electronic health record, extract the relevant information, and then reason that, oh, this is the code that will apply. So that's exactly what we do. And we work with a company that actually in this business, and near 100% accuracy they could achieve, and it's actually deployed in the field, used, and then building reliable chatbots. So if we use an LLM for a chatbot, who knows, where the conversation will go. So we do the same thing from the text, and I'll give an example, the next 2 slides, and then I'll be done. So given a sentence, we extract the knowledge, and then we process it, using the reasoner and common sense knowledge that we already possess. So we build task bots, social bots for conversations that don't go, off track, and even, automating, for example, the drive-through of a Taco Bell. And that's a problem that many have worked on. So, for example, you might remember that McDonald's canceled this project working with IBM. That's because if you rely too much on machine learning, you can hallucinate and, may produce incorrect responses. So it was suggesting, for example, bacon bits as ice cream topping or something. But if you use a combination of machine learning and reasoning, you can achieve 100% accuracy. So we can build, bank tellers automated, or airline reservation agent. And in fact, there is a company that is, working with us on building a chat bot for counseling parents of ADHD kids. So again, when the parent says a sentence, knowledge is extracted, and then reasoning engine is used to figure out. And then, so the large language model is used only for translating text into predicates, compute with these predicates, compute a response as a predicate, and then reverse translate the predicate into English. That seems to work extremely well. And of course, in medical field, if you use a chatbot, especially in counseling, then you have to be very careful. There have been news where, kids committed suicide after talking to, chatbot based on large language models. Advanced automated software certification, we've used our system for that as well. Automated legal reasoning, and in fact, SCASP analysis was used to find error in Singapore law. And autonomous driving as well. So that's an, aspirational project that we keep working on. And if you think about autonomous driving, then as a driver, we actually don't, just use pattern matching. We actually use reasoning. We say, oh, I see a red light, I must stop. I see a pedestrian and a zebra crossing, I must stop, right? Or I must slow down or whatever. So the idea is that you use a combination of machine learning and reasoning, or, for example, building autonomous drones. So we actually have simulations where you process the picture, convert it into knowledge, but then process this knowledge to make actions, compute navigation actions. So we actually build simulations where a drone can be instructed to essentially go around a building. It's just like a human would do, right? If we are controlling a drone, if we don't get a good look at what we are seeing, we might say, oh, fly, like a little bit further or closer and take another look, sort of thing. Can we do that autonomously? And it's possible. So here is, again, already explained this press release on using combination of large language models and reasoning for extracting medical codes with near 100% accuracy, as I said, deployed in the field and so on. And then finally, just another 2 minutes and I'll stop. Building chatbots that understand. So give you the example. So this is a chatbot that recommends restaurant, like a hotel concierge. So in a hotel, you go to the concierge and say, hey, can you recommend me a restaurant? Then think about the knowledge that the concierge must have and the questions the concierge must ask. The interesting thing is also that as humans, we give variable amount of information. We might say, can you recommend me a restaurant? Or we might say to the concierge, can you recommend me a Chinese restaurant? Or we might say, can you recommend me a cheap Chinese restaurant for, me and my wife, and we have our anniversary, for example, today. So each, utterance gives variable amount of information, and this will affect the decision that the concierge will make in terms of making a recommendation. So we extract all that as knowledge. So first we have to decide on a vocabulary or ontology. So what is the ontology corresponding to, say, restaurant recommendation? Restaurant name, we should have cuisine type, right? price range, family friendly or not, and then whether you prefer something. For example, oh, I like sushi, then I must recommend a Japanese restaurant. Then I must have common sense knowledge, which is, of course, database of local restaurants. And then knowledge such as if you say I prefer curry, then I should recommend Thai or Indian restaurant, for example. Or if you say I like sushi, then recommend a Japanese restaurant. So, so actually converting text into these these ontological predicate terms, you get very high accuracy from LLMs because it's a pattern matching process. It's language to language translation task, right? So, for example, I'm looking for a restaurant that serves curry, then this is what LLM will generate. And then knowledge about what to ask, and depending on the knowledge I have, is coded in SCASP. So essentially, you can think of it as to recommend a restaurant, I need to know preferred cuisine, price range, family friendliness of the restaurant, and this is all implemented as ASP rules. And so we look at the knowledge we have and then figure out what to ask next. And then, of course, we can give justification for each recommendation. And the computed response is a predicate converted into text with an LLM using reverse parsing. So here's an example interaction. And these are all working chatbots, and you can find all the code and everything on my homepage, including a social bot. So hi, how can I assist you? Can you say, can you recommend me a restaurant? And it extracts these predicates. Ignore the format. And then I know that you want a restaurant and you're querying about the name of the restaurant, basically. And then I know that I have to ask you various. But had you come and said, can you recommend me a Chinese restaurant? I would have extracted that the cuisine type you're looking for is Chinese. There'll be another predicate that will capture that. And then I would know not to ask you about your. So I say, I can try any food except curry. And then I basically, generate with some reasoning that you don't want Indian or Thai. Are you looking for a certain price range of restaurants? They say less than $15. And I'll extract that your price range is cheap. So the interesting thing is that, and that is where LLM shine, that is, if they said, what's the price range? You say, I'm a student, then it will say price range cheap. Anyway, so you can basically complete the whole interaction and whole interactive system. Okay, conclusions. So basically, machine learning and generative AI are impressive technology, but they are pure pattern matching devices with no correctness guarantees. So we want to address the problem of developing reliable AI system. So we argued that reasoning is indispensable. So we use machine learning to convert sensory input to knowledge, and then use ASP and SCAS to reason with this knowledge. Now, the downside is that the system built will be domain specific. And then, of course, you have this big problem of how to scalably represent common sense knowledge. But if you want trustworthiness and explainability, there is no way out of this, I believe. So our work is essentially to build this CAS system and develop many of its applications. And thank you. And I think I have probably left only 2 minutes for questions.
Okay, thank you. And still, we do have 2 minutes for questions. Anybody? Okay. Dr. Gupta, thank you very much. I just want to make one comment. System like yours that actually can provide reasoning would be much more attractive for our audience. We have more than 20, at least 20 actively used decision intelligence platforms right now. And you've seen, for example, yesterday presentation by IBM, who are very, very interested in reasoning systems. So if a system like yours could partner with one of the vendor or two or several vendors of decision intelligence platforms, this would be something more practical that we can try, we can use, because it's already, you demonstrated some good reasoning facilities, and it's interesting to incorporate them in more generic platforms.
Absolutely. And the system is open source, and I'm very happy to help anyone who wants to use the system. As I said, there are companies, small numbers that have actually they're using it or have used it for human style reasoning, basically.
Okay, thanks a lot again. Thank you very much.
Okay, and thank you. Thank you, everyone. And my email address and everything was there, so feel free to send me email. Okay.
Okay.